In this lesson, we are going to continue our study of confidence intervals for proportions. So in this section, we are going to form confidence intervals for the difference between two population proportions. For example, you might want to know if there's a difference between the proportion of people who recover after taking a drug versus those taking a placebo. So the notation for this from before is P1 minus P2 if you know the true proportions, or P1 hat minus P2 hat if you have estimates of the proportions. But the point is there are two separate groups to which meet a different criteria, say they're Republican or not, or have had something different done to them, taken a drug or placebo. And we're still going to use the general formula for confidence intervals, which is the sample statistic plus or minus our multiplier times the standard error. And in each case that we're going to have, the sample statistic and the standard error sort of change based on the context, but that multiplier will be the same as in the previous section. So in this case, the sample statistic is P1 hat minus P2 hat. So the difference in those two proportions. The standard error of P1 hat minus P2 hat is the square root of P1 hat 1 minus P1 hat all over N1 plus P2 hat 1 minus P2 hat all over N2. And use the same values of Z star as in the previous section. In the 2008 General Social Survey, participants were asked what their main news source is. Among those surveyed in the 18 to 29 year age group, 92 out of the 262, or 35%, said the internet was their main news source. In the 50 and over age group, only 59 out of 632, or 9.3%, said the internet was their main news source. We're going to determine a 95% confidence interval that estimates the parameter P1 minus P2, which is the difference between the population proportions who use the internet as the main news source in the two age groups. We're going to use the 19 to 29 age group and minus the 50 and over age group. Okay, so your first step you should do is you should find your sample statistic. In this case, that's P1 hat minus P2 hat. So P1 hat is the proportion who use the internet in the 1929 group. That's 0.351 minus the other age group, which is 0.093, or 0.258. Next, let's find the standard error of the sample statistic. So standard error, sample stat, which is the standard error of P1 hat minus P2 hat. So we have the formula given above, so I'm not going to write it over. So it's P1 hat, so that 0.351, times 1 minus P1 hat, so 1 minus 0.351, all over N1, and you see this is the first size, 262, plus the other proportion, which is 0.093, 1 minus 0.093 over N2, which is 632. And this comes out to be approximately 0.0317. And note that 7 means we're going to round up to about 0.032. Let's just use 3 decimal places here. And then our 95% confidence interval. So is the sample statistic P1 hat minus P2 hat, which is 0.258, plus or minus, for 95% confidence intervals, we just use 2. So 2 times 0.032. So that's 0.258 plus or minus 0.064, or 0.194 to 0.322. You can also give these things as percents as well, so you could say 19.4% to 32.2%. Either one of those is fine. And it just wouldn't hurt to write a summary, so let's write a summary sentence about what this means. So with 95% confidence, the difference between the proportion of 18 to 29-year-olds who use the internet as the main news source is between 19.4% and 32.2% higher than the 50 and over group. Note, you could have said the difference in proportions was between those numbers as well. That wouldn't have been wrong. But it is the case that this is definitely suggesting that young people use the internet much more than people over 50. Okay, when finding a confidence interval for the difference of two population proportions, when will your interval give you evidence that the difference in these two populations is 0? And when will the interval give evidence that the difference is not 0? Okay, so we want to know under what circumstances is it likely that we're going to see that it's P1 minus P2 equal to 0. And that would imply these proportions are equal. Okay. So we will have evidence that this difference might be 0. If 0 is included in the confidence interval. There could be other reasons for that as well. I mean, it could be that your confidence interval is super wide because your sample size is really, really small. So that might be it, but it also is possible that the difference may have been 0 and those proportions are equal. And similarly, evidence that the difference is not 0 occurs when 0 is not in the interval. So evidence that the difference is not 0 if 0 is not included in the interval. Like in the previous example. In that example, our interval went from 19.4% to 32.2%. 0 was not included, suggesting that those two population proportions are actually different. In a survey of college students, 70% of the 100 women surveyed believe in love at first sight, while only 40% of the 80 men surveyed said they believe in love at first sight. Use men minus women. So we're going to find a confidence interval for this difference, and we'll just break it up into little pieces. So first, find the value of the difference between sample proportions for men and women. So P1 hat minus P2 hat. So we're going to do women first. That population estimate of the population proportion is 0.7 minus 0.4 for an estimated difference of 0.3 or 30%. Find the standard error of the difference between the sample proportion. So the standard error of P1 hat minus P2 hat. Big old root sign. Okay, P1 hat 0.7. 1 minus 0.7, which you could say is 0.3, over 100 plus 0.4, 1 minus 0.4 over this sample size was 80. So that comes out to be about 0.0714. And notice this 4 means we can just leave that 1 alone. So approximately 0.071 or 7.1%. So now we have all of the necessary information needed to find this 95% confidence interval. So let's find that approximate 95% confidence interval for the difference between the population proportions believing in love at first sight for men versus women. So the general formula here is P1 hat minus P2 hat. That's our sample statistic. Plus or minus 2 times the standard error of P1 hat minus P2 hat. So sample statistic plus or minus our multiplier times the standard error. So that's 30% or 0.3 plus or minus 2 times 0.071 or 0.3 plus or minus 0.142, which is 0.158 to 44.442. So that's one possibility if you give them as proportions, or as percents, we could say 15.8% to 44.2%. On the basis of the confidence interval found in Part C, is it reasonable to conclude that there is a difference in the proportions of all college men and women who believe in love at first sight? Explain. Well, an interval does not contain 0, so yes, I think it does. So yes, the interval does not contain 0, which means 0 is not a plausible value, which means those two proportions can't be equal. So yes, the interval does not include 0. This suggests P1 minus P2, as in the true proportions, are not equal to 0, which implies that P1 is not equal to P2, as in the proportions are different. And we can say that with 95% confidence, the difference between between men and women who believe in love at first sight is between 15.8% and 44.2%. You could also say that the difference is that much higher in the female group, between 15.8% and 44.2% higher among females. So the last section in this chapter talks about using confidence intervals to guide decisions. So, for example, a value that is not in a confidence interval can be rejected as a likely value. So if the confidence interval gives the plausible values, and that one is something is not in your interval and therefore it's not plausible. So for example, 0 in the last example, we were able to reject that as a plausible value as it was not inside the interval. When a confidence interval for a difference in proportions does not cover 0, it's reasonable to conclude the two proportions have different values. Or if you have two confidence intervals for proportions in two different populations and they don't overlap, it's reasonable to conclude that the population proportions are different. But if your intervals do overlap, no conclusion can be made and a confidence interval for the difference should be computed. And here's that as a picture. Suppose, this is 0.1 up to 0.9 or something. In one interval from 0.1 to say 0.3, another one from 0.6 to 0.9 for some different proportion. Well, the first interval is the list of plausible proportions for the first variable, and the second is the list of plausible values for the next variable. And since they share no plausible values, the true values are likely to be different. A Gallup Organization poll of 1,012 randomly American adults in November of 2011 found that 56% of those surveyed felt their weight was about right. The margin of error for this survey was given as 3%. Find a 95% confidence interval estimate of the percentage of American adults who thought their weight was about right. So you could go through the motions and compute a more specific value of the standard error here, and let's go ahead and do that. Just check and see how right their 3% margin of error is. So first of all, our p hat, our sample statistic, is 0.56. Then we'll find the standard error of p hat. Notice we're back in p hat territory because we have one group of people. There's no second proportion. The 3% is the margin of error. So 0.56, 1 minus 0.56 over 1,012. That's about equal to 0.0156, which we're going to round to 3 decimal places as 0.016. So our 95% confidence interval is given by 0.56 plus or minus 2 times 0.016, which is 0.56 plus or minus 0.032, and notice that that's your margin of error, which is awfully close to the 3%. And this is 0.528 to 0.592. So that's one way to give your answer in proportion form, or as percents. You could say 52.8% to 59.2%. On the basis of the confidence interval you computed in Part A, explain whether it's reasonable to say that more than 50% of American adults at that time thought their weight was about right. So notice that this interval is entirely above 50% and doesn't contain 50%. So as this interval is entirely above 50% and does not contain 50%, we can reject 50% as a plausible value at the 95% confidence level. A November 2011 Gallup poll of this same individuals, this is kind of the same study. So in 2011, 56% of US adults felt that their weight was about right. And then a similar poll in 1990, 46% felt that their weight was about right. And the margin of error for each poll was 3%. For this one, because we found the margin of error was so close to 3% in the last one, we're just going to use 3%. Also, they don't give us the sample size for the 1990 people, so I think that just assumes that 50% is, or that assumes we're just going to use this margin of error. Okay, so let's find confidence intervals based on these margin of error, kind of chapter 5 style. Confidence interval for 2011 is about 56% plus or minus the 3% margin of error, or 53% to 59%. And the confidence interval for 1990 is 46% plus or minus that 3%, or 43% to 49%. Which is ironic because fewer people in 1990 were actually overweight as proportions, so that's a little bit interesting. So based on these results, is it reasonable to conclude that the population proportions were different? And what you should observe is that these intervals don't overlap. So the plausible value for the true proportion in 2011 can't be in the plausible values range for 1990. So there you go, yes. These intervals do not overlap. Suggesting a difference. Difference. In these two proportions. Assuming the sample size was 1,012 for both polls, find a 95% confidence interval for the difference in the population proportions. And just note that we're going to use 2011 minus 2009. We're going to use that order so we keep things positive. Okay, so first thing, P1 hat minus P2 hat. So now we know these proportions are different, and the question is approximately how much. So that's 0.56 minus 0.46, which is 0.1, or 10%. Then find the standard error of P1 hat minus P2 hat. Okay, 0.56, 1 minus 0.56, over 1,012. And we assume the population, or the sample size for the 90/90 thing is also 1,012. And that's 0.46. 1 minus 0.46. Comes out to be approximately 0.022 or 2.2%. Okay, 95% confidence interval is 0.1 plus or minus multiplier of 2 times 0.022, which is 0.1 plus or minus 0.044, or 0.056 to 0.144, which as percents, I just think they're easier, 5.6% to 14.4%. So on the basis of the interval that you found in Part B, formulate a conclusion about whether the population proportion was different in 2011 than 1990. Write your conclusion in words that would be understood by somebody with no training in statistics. So we should say our confidence level. So with 95% confidence, we can say that the proportion of people who felt their weight was about right was between 5.6% and 14.4% higher in 2011 versus 1990. The proportion of people who felt their weight was about right was between 5.6% and 14.4%. Higher in 2011 compared to 1990. On January 30th, 1995, Time magazine reported the results of a poll of Americans in which it asked, have you ever driven a car when you probably had too much alcohol to drive safely? Of the 300 men who answered, 189 said yes, and 111 said no. Of the 300 women who answered, 87 said yes, 213 said no. Compute the 95% confidence interval for the difference in the proportions of American men and women who would say yes to this question. So it seems like men said yes quite a bit more often, so let's figure this out. So question 1, first find the difference in the proportions. Well, 189 out of 300 men said yes, minus 87 out of 300 women. Those are 0.63 minus 0.29, which comes out to be 0.34. Next, find the standard error of P1 hat minus P2 hat. And that's where we're going to use these numbers. Note that P1 hat is 0.63, P2 hat is 0.29. So we have 0.63 times 1 minus 0.63 over N1, which is 300, plus 0.29, 1 minus 0.29, also over 300. This comes out to be about 0.038. So now our 95% confidence interval is given by the sample statistic, which is 0.34, plus or minus the multiplier, which is 2, times 0.038. So that's 0.34 plus or minus 0.076, or 0.264, to 0.416, which you could also express as a percent, 26.4% to 41.6%. So write a sentence or two interpreting this interval. So with 95% confidence, so always start by stating your confidence level. So we can say that the interval that we have covers the difference between the proportions of men and women who would say they have had a drink, have driven after having too much to drink. So 95% confidence, we can say that the interval (26.4% to 41.6%) covers the difference between the proportions of men and women in the population who would say they have driven after having too much to drink. Can you conclude that these two proportions actually differ in this population? Well, this interval certainly does not include 0, so yes. So yes. The confidence interval does not contain 0. It really isn't even close. And we estimate with, say, your confidence level, 95% confidence, that the proportion of men in the population who would say they have driven after having too much to drink, would say they have driven after having too much to drink. Is between 26.4% and 41.6% higher than for women. All right, last one. The professor wants to know whether her class of 60 students would prefer the final exam to be given as a take-home or an in-class. She surveys the class and finds that 45 of the 60 students would prefer a take-home. explain why she should not use a 95% confidence interval for the population proportion preferring a take-home exam. So first of all, who are those 15 students who voted against this? Who knows? So the kicker here is that we don't have an estimate. We actually have the true proportion. So unless she has other classes, this class is her entire population. So the professor's class is the entire population of interest. And is not a sample from a larger group. And what that means is that you don't have to try to estimate the population proportion, you know it. So you know the exact proportion. Who prefer a take-home exam, i.e. P, not P hat, is 45 out of 60. And there's no need to estimate it. Okay, well that's it for chapter 10. So confidence intervals for proportions.